So ultimately, once we have the linear algebraic equation, the set of equations, we'll try to solve them. Now we'll see a more specific example for this. As I mentioned to you, a 1D heat conduction equation represents such a diffusion equation without the advection term, without the unsteady term. So it's a steady state one-dimensional conductive heat transfer equation. The property phi is actually being replaced by temperature T, and the conduction coefficient K is representing the diffusion coefficient in that case. And the source S can be, let's say there is electricity passing through it, or there is another source, a chemical source or some other source by which heat is also getting input into the domain. So when we try to put in some numbers, let's say I put the one side of the rod at a temperature of 100 degrees centigrade or Kelvin, and the other side on 500 Kelvin. Actually in this case it is Kelvin. So let's say I put one end of the rod at 100 degrees Celsius, and on the other side I have 500 degrees Celsius. So these are the boundary conditions, unique values, the Dirichlet boundary condition as I mentioned earlier. We have a cross-sectional area which has been provided, and we have the conduction coefficient also being defined. So with these unique values, when we try to obtain the set of linear algebraic equations, so I'm solving the temperature equation, the energy equation more specifically, and when we try to obtain the linear algebraic equation, we can obtain this without any problems on cell number 2, 3 and 4, because these are bounded by cells on the western side as well as eastern side. And the equation which we have from the previous discussion, so I'm just applying that sort of equation, and instead of gamma we have k, and delta x of course is defined by what is the size of the grid which we have defined. In this case I'm dividing the domain in such a way that I have delta x of a value of 0.1 meters, and we apply this for the cells which are inside, which is cell number 2, 3 and 4, and we obtain a generalized linear algebraic equation. That was pretty straightforward. The problem actually arises for cell number 1 and 5, because these are at the boundaries, because they do not have cells either on the western side or on the eastern side for cell number 1 and 5 respectively. Therefore, we have to obtain a different sort of equation. So as you can see here, we have on the eastern face for cell number 1 there is no issue. We can write Te minus Tp upon delta x. But on the western side there is no cell behind cell number 1, so therefore we have to use the boundary condition here. So we have Tp minus Ta upon delta x by 2, because we are not going on to the other cell center, but we are only having half of that distance. So in that case, when we apply it, we obtain a different form of the linear algebraic equation with coefficients a bit different. So in this case, as you can see here, there is no cell on the western side, therefore the coefficient is 0 in this case. But we do have cell on the eastern side, which is cell number 2 for cell number 1, and we have AP defined in this way, and we have, in this case, as you can see here, SP has a non-zero value. So when we apply this over the cell number 5 now, which doesn't have a cell on the eastern side after the cell, so we have in that case the eastern cell which doesn't exist, therefore we have the boundary condition Tb minus Tp upon delta x upon 2. Similar treatment to cell number 1 on the western side, we have it here on the eastern side, and the other term remains intact. And in this case, as you can see here, the coefficient Ae is absent, although there is a cell on the western side which is cell number 4 here. Mind you, the whole geometry has been divided into 5 cells, and therefore we have these issues with cell number 1 and 5 which are on the boundaries. The rest of the terms look similar to cell number 1, as you can see, SP and SU. And ultimately, when we collect all the terms together, we obtain now the set of linear algebraic equation for the temperature at the 5 grid points. As you can see here, we have 5 equations being after having applied them on the 5 cells. So we have 5 equations, we have 5 unknowns. It should be a perfectly solvable system of linear algebraic equations, and we obtain the solution which corresponds quite exactly to the exact solution, which you can do by simple integration. When we convert these equations that you see on this slide here, on slide 22, when we apply them in the form of a matrix, and then we try to invert the matrix or in some way to solve them, we obtain the temperatures T1, T2, T3, T4 and T5 at all the 5 points with the boundary conditions also remaining intact. We obtain this solution. So this is the typical approach. What we have managed to do is also in the case of a two-dimensional problem, we do something similar. We manage to convert our partial differential equation into a linear algebraic equation. So in the 2D case, as you can see here, instead of just the cells on the eastern side, on the western side, we have also cell on the northern side and southern side. Now what you see here is a structured grid, and that's why what I mentioned in the outline already, that we are looking at a structured formulation of the finite volume method for this diffusion problem, and I'm also going to speak about the convection diffusion problem. In both cases, we are looking at a structured grid. Now when we apply this, just the number of neighborhood terms increases. You also get the southern cell value phi s and phi n also coming into picture, but the overall philosophy of having a linear algebraic equation remains the same. That's the same with a three-dimensional problem. So in three-dimensional problem, the diffusion and source term, in this case, as you can see here, the diffusion term has three components, and accordingly the three components also mean that we have cells on the southern side, northern side, eastern and western side, and as well as top and bottom side. So again, it's a structured mesh that I'm speaking about, a structured solver formulation. What we obtain in all the cases is that we have the value of the cell phi p being expressed in terms of the neighborhood terms and a source term. So that was quite straightforward for a diffusion equation. We have managed through the finite volume method to convert our governing partial differential equations into a set of linear algebraic equation for a diffusion equation. Let's look at what happens for a convection diffusion kind of an equation. So we're going to look at the convection diffusion equation, which we already saw in the finite difference method lecture. And what we have in this case is, like, additionally we are considering that it should satisfy the continuity equation. It's a one-dimensional problem again. Here we have the velocity field u, which is flowing in this direction. The fluid is flowing in this direction. That's why it's a convection diffusion equation. It doesn't have a source term here, and I'm considering a steady state formulation. So we have the advection term here, and we have the diffusion term here. It's a one-dimensional problem. It pretty much looks like an ordinary differential equation, but because we want to learn finite volume method, let's start with a one-dimensional form, and we'll move on to the partial differential form for two-dimension and three-dimension later. Now again, what we have done here is that we have converted our equation for both the advection and the diffusion term into the discretized form of the equations. We have phi rho u a phi on the eastern phase and on the western phase, and we have the diffusion term on the eastern and western phases. Now this is because we have these equations in this differential form. We convert it into the integral form and obtain the surface integral form, and then when we apply it over the discretized geometry, after applying it over the discretized geometry, we obtain something similar to what we had already seen, that we have the quantities on the eastern and the western faces. And when we also apply this integration over the continuity equation, for the continuity equation we obtain the rho u a on the eastern phase, which is simply mass flux across mass flow rate across the eastern phase and the western phase. The difference between them is equal to 0. We'll just use some notations to make our representation a bit more simplified. So we represent flux F by rho times U. So rho times U is something like mass per unit area per unit time. So mass flow rate per unit area, that's mass flux. So we have F defining the mass flux on the eastern phase and in the western phase, as well as capital D being representing gamma upon delta x. Now this delta x is something which comes because of your grid. So the finer the grid, the bigger the value of this d. We try to apply this and we obtain an equation of this form. The areas, let's say, on both sides get cancelled. We assume that the area of the different faces is the same for a one-dimensional problem. So we have flux E is equal to flux W according to the continuity equation, and for the general transport equation we have phi E and phi W, as well as on the eastern and western faces, mind you, you can see here we have small subscript small e and small w compared to the cell centroid values, which are represented by capital E and capital P and capital W. So you'll see this difference as we go further. The question comes how to represent this phi small e and phi small w, which is the value of the property phi on the eastern and western faces, in terms of the cell centroid values. Now that is why we have something called the phase approximation techniques or the discretization techniques. I'm going to speak about upwinding schemes just in a minute, but what you can see here is the equation when we try to obtain the phi e and phi w in terms of the cell centroid values. We obtain an equation of this form, which on further simplifications yields something similar to what we are already familiar with, which is AP phi p is equal to all the terms in terms of the unknowns of the neighborhood and multiplied by their respective coefficients. And these coefficients can be tabulated as we have already seen. We'll see this more specifically now through an example. But before that, just to illustrate to you the part of convection and diffusion term, what you can see here is that we have taken phi at the eastern phase and on the western phase expressed as a simple average between phi p and phi w. That's a central differencing scheme. But in reality, let's see what happens. In reality, any fluid, if it flows, if its convection term or the advection term is dominant, what it means is any property phi is completely convected by the velocity field. On the other hand, if it is a purely diffusional flow, there is no velocity field driving the fluid, in that case it purely gets diffused without any convection effects. But usually what we encounter is a combination of both the convection and the diffusion terms. So we need to give more account to the value at a phase. We need to give more preference, or at least a bit more preference compared to the cell downstream. We should give preference to the cell which is upstream, and that's why we get these schemes called the upwinding schemes. So what we did in the previous slide, that we applied phi e simply in terms of a simple arithmetic average of the cell centroids surrounding this phase. This is fine if the flow was completely diffusional, but as we can see here in the next slide, the usual phenomena is that it's a combination of diffusion and convection. So we need to give the value at, let's say, this phase to be a function of the value at cell 1 and cell 2, maybe even previous cells, but I should give more preference to the cell which is upstream. And that's why we have the upwinding schemes coming into picture. So in any solver, for any equation that we are solving, we need to choose an appropriate upwinding schemes. Now this list might look a bit daunting for you at the present moment, but we'll be looking at it more exactly when we deal with the solver mathematics. We have a variety of schemes by which we can define how the value at the cell phase should be expressed in terms of the cell centroid values surrounding the phase. So we have schemes like first order upwind, power law, second order quick scheme, and still very many in the list. But we are going to look at some of these, the first four which have been listed in this the list of the schemes. We'll start with the first order upwind scheme. The first order upwind scheme actually will be very good assuming that the flow is highly convective. So what it says is that the flow is highly convective, so the value at a cell phase is equal to the value at the cell which is just preceding it, that is just upwind of it. So basically the value at the phase is represented by the cell which is upstream of it, so the velocity field direction is quite important in this case. It only gives a first order accuracy, and it is quite good for high speed and low diffusion flows, which is inviscid flows, but which is not usually the case. Therefore we have a better scheme called the power law scheme, which actually applies the one-dimensional convection diffusion equation solution to represent the value at the phase. So that comes in terms of a number called the Peclet number. So if Peclet number is a relative ratio of the convection and the diffusion term, so if we have a flow which is highly convective, then in that case Peclet number is close to infinity. So in that case the value at the phase will be equal to the value of the cell which is just upstream of it. That's similar to the first order upwinding formulation. And in the other case, if let's say we say the Peclet number is tending to 0, that's when the diffusion term is dominating as compared to the advection term. In that case, we have a simple diffusion equation. That's as good as what we did earlier, a simple averaging of the two values across the face, the values at the cell centers across the face. Another scheme which has a higher accuracy is called the second order upwind scheme. It uses some gradients, and there are some methods by which these gradients are calculated. So you don't just account for the cells which are just surrounding the face, that is the cell centroids surrounding the face, but we also take into account one cell before the the just upstream cells. So therefore you have a greater accuracy being brought in, second order upwinding scheme. And we have still a third scheme which gives in a third order accuracy, which is called the quick scheme, which is quadratic upwind interpolation for convective kinetics. This is considered to be the most accurate scheme, but there are some restrictions to the scheme, that it requires that you can only apply it on quadrilateral and hexahedral meshes, quadrilateral in 2D and hexahedral in 3D. So we can apply it only over those kind of meshes. If you have a combination of hex and tet mesh, that's a hybrid mesh, I'm going to speak about it, how the quick scheme can adjust itself also to cater to such kind of problems. So it gives us a third order accuracy. It's more accurate than the conventional first order and the second order schemes. And what the quick scheme does is, like as you can see here, it has a blending factor theta, and based on this theta you switch between the central differencing scheme, that is the simple averaging scheme, and the second order scheme. So it's a blend of the central differencing and the second order upwinding scheme, which gives it a third order accuracy. The traditional quick scheme which has been reported in the literature has the theta value, the blending factor, being restricted to 1 upon 8, but what is typically employed in solvers like Fluent is a value of theta which can vary itself to stabilize the problem. So it can switch over from if the problem is very highly diffusive, then it can switch over to a value of theta which would make the problem quite diffusive. So that is theta tending to a value of 1. And in the other case, when we want to obtain the second order upwinding value, if the flow is quite highly convective, in that case theta can go as low as 0. So this is how typical solvers like Fluent or also CFX try to vary the value of theta and obtain a solution appropriately. So these were the different upwinding schemes to take into account how the phase values coming up because of discretization of your advection term, how these values have to be expressed in terms of the cell centroid values. So as you can see here, the quick scheme will be typically more accurate on structured grids where the grid is aligned along the flow direction. That's why we try to obtain very good flow aligned grids or mesh. But solvers like Fluent also allow the use of quick over a hybrid grid. So in hybrid grid you have a combination of hexahedral and tetrahedral elements in 3D, or a quadrilateral and triangular meshes in 2D. So in such cases it can switch over between the quick scheme being applied for hexahedral mesh or the quadrilateral mesh in 2D, and for the unstructured elements like tetrahedral in 3D and triangles in 2D, the second order upwinding scheme is applied entirely. So solvers like Fluent are intelligent enough to take into account such hybrid meshes. So I hope you could follow the lecture today about finite volume method, how we are able to obtain from the partial differential equations a set of linear algebraic equations, and we combine all the linear algebraic equations and we try to obtain a solution for a given transport property phi, and this can be done for all the governing equations. I hope this lecture was helpful for you to get a bit more insight into the numerical scheme which is applied in the commercial software packages like Fluent, CFX, or any other software which is available in the market. Thank you very much for your attention. Goodbye.